Hello and welcome to page 2 of the Fall 18 Exam 2A for Chem 8A. If you are looking for version B, you can find that in a separate video. We're going to add curved arrows to show the mechanism in each of the following reactions. We can make a nice little list for each of these of bonds broken and bonds formed. And that'll help us start and end our arrows in the right spot. First of all, we see from our starting material that this oxygen has a negative charge and is connected to one carbon. If we look at that same oxygen in the product, we see that that is now bound to 2 carbons. So that tells us we need to make a new carbon-oxygen bond. Okay, and then if we look at our other reactant, if we look at this carbon that was connected to a bromine, we can see that that bromine is no longer attached, and that carbon, as we just mentioned, it has a new bond to oxygen. So in particular, once again, we're going to be breaking the carbon-bromine bond, and that's going to be some important steps to make sure we're ending and starting at the right place. Electron movement always goes from the electron-rich region to the electron poor region, meaning that's where our arrows, the electron-rich area is where our arrow has to start, and that's going to be this negative charge. Whether or not you draw the lone pair on oxygen doesn't matter. We're going to start at that oxygen, and we're going to end at carbon. That means that we're going to be forming a carbon-oxygen bond. At that point, we now have too many electrons around that carbon that was just attacked, so we're going to start at the bond, in the middle of the bond, and end at the bromine. And so that tells us that we're going to be breaking the carbon-bromine bond. Check. And that's how we do that. This, by the way, is called an SN2 reaction. You're going to learn about this relatively soon in Chapter 11. These are problems that I took directly from, I believe it was the Chapter 6 homework set. Right. Next, we look for the broken and formed stuff in the starting material to product. So actually, we want to do this step by step, and we can see in this region of the aromatic ring, this region of the aromatic ring, we have that hydrogen, which is highlighted. It's still there in the intermediate, but the thing that's different in this particular step is that we're needing to break specifically the carbon-carbon pi bond. That's going to be part of it. The other thing that's happening in the other reactant is that we have a bond between deuterium and chlorine that is no longer there. We can see it's split. So not only do we need to break that pi bond, we're going to need to break the DCO bond. And in the process, we're going to form a bond between carbon and deuterium. And by that I mean we're going to be forming that bond between this carbon and this deuterium right there. So let's do these one at a time. Rather than moving on to the next step, we're going to start at the pi bond that we're going to break. We're going to start right at the middle of it, and we're going to end at the deuterium. And that means we're going to be making a new carbon-deuterium bond while in the process of breaking the carbon-carbon pi bond. Next, we're going to be starting at the middle of the DCl bond and ending at the chlorine. Check. In the second step, we'll see what else is different. We notice that there's a carbon-hydrogen bond in the intermediate that is no longer there in the product, and that hydrogen is now bound to a chlorine. So we'll use that information to start our list that we're going to be breaking a carbon-hydrogen bond, and we're going to be forming a hydrogen-chlorine bond. We'll look for other differences in the starting material to product, and we will find that here we have a carbocation next to a single bond. Now there's no more carbocation, and now that is a double bond. So that's going to be a pretty big deal, things that we need to do. We're going to be forming a carbon-carbon pi bond. Again, we go from electron-rich to electron-poor. We're going to start at the electron-rich, negatively charged chlorine, and we're going to end at the hydrogen. And we knew that once again because we were trying to form a hydrogen-chlorine bond. So we start at the chlorine and end at the hydrogen. We need to break the carbon-hydrogen bond, which means our arrow has to start at this bond right there in the middle and we need to form the carbon-carbon pi bond, so we're going to kick these electrons right down, kind of a small arrow, once again breaking the carbon-hydrogen bond in the process of forming the carbon-carbon pi bond. And that's how you add the arrows for those two reactions. Next, we're going to be following the arrows. This is another homework problem from chapter 6. And let's give a nice little description for what each arrow means before we draw those products. The first arrow here, being the first arrow, means that we're going to be, it starts at an oxygen and ends at a carbon. So that means we're going to be forming a new carbon-oxygen bond. That's what that arrow means. The next arrow starts at the pi bond and ends at the hydrogen. That means we're going to be forming a new carbon to hydrogen bond. The next arrow starts at the OH bond and ends at the oxygen, and that one means we're going to be breaking an oxygen hydrogen bond. So that's the main stuff. I realized I forgot to mention another thing about this purple arrow. Because we're starting at the pi bond, that means we're going to be breaking that carbon-carbon pi bond. So that should be our tally of things to do. I'm going to start in this next box by drawing all of the stuff that shouldn't change. And so by that, I mean, I'm going to keep all of these carboxylate groups, all of this carbon chain here, all exactly the same. Those guys didn't go anywhere. Okay, and now we have a new bond between, I'll make that different color. I'll make this now a new bond between this carbon here and that oxygen. That oxygen is still connected to two hydrogens, and now since oxygen has 3 bonds, it should have a positive charge, so we'll label that. Once again, we broke the carbon-carbon pi bond, so that's going to remain a single bond. However, we do have a new bond to hydrogen, which doesn't necessarily need to be highlighted, but for the sake of this problem, I will. There's a new hydrogen right there. And that takes care of most of it, but remember that we have to consider what happens to that hydronium molecule. And all that happened is that we lost one hydrogen, which means what we have left is H2O or water. And those are the two products that are the result of those arrows. So this is more down below, more examples for arrow pushing in the context of carbocation rearrangements. And the starting material and product are given, or the starting intermediate and product are given. But what you'll notice in both cases, the reason why these happen is because you end up with a more stable carbocation or a more stable molecule. The first one, we start at a secondary carbocation and we end at a tertiary carbocation. Remember, it's not the carbocation itself that's moving, but in this case, it's some other form of electrons that are moving and causing the positive charge to be in a different spot. Now, the main thing that may be missed is the fact that this carbon here also has one hydrogen. This carbon here, funny bond angle, has one hydrogen. If you look at the product, this one, since it has the positive charge, doesn't have that hydrogen anymore. But now over here, this one has 2 hydrogens. So that's a really big deal, and really just to highlight the one that's different, we have the tertiary hydrogen moving over to the secondary carbon. I'll zoom in so you can really see. Maybe I won't zoom in more because I can't. There we go. So we can really see where this arrow is supposed to start and end. It would start at the carbon-hydrogen bond and end at the carbocation. That means that this hydrogen leaves and it takes its electrons with it. And we call this a hydride shift. Good thing to remember that a hydride is an H- ion. It doesn't really exist on its own, but that's essentially what's moving is the hydrogen with its 2 electrons. Let's now then move over to this problem here. This one starts at a tertiary carbocation and ends at a tertiary carbocation. But the reason for this shift is because we have a nearby quaternary carbocation, thus making this a 6-membered ring, which is more stable than a 5-membered ring due to angle strain and or ring strain. So we want to take a look at the different stuff, meaning what's moved, and we'll see here that we have, once again, the obvious 5 to 6-membered ring rearrangement. I'm just going to go ahead and number these carbons. I'm doing it sort of arbitrarily, like this isn't how we would name it or number it to name it, but these are going to be our reference points for our next compound. The real reference point, in my opinion, are these two methyl groups, 1 and 3, and I'm going to label those on the structure. These are the two methyl groups that are connected to the same carbon. So I can start by numbering 1, 2, and 3. And we're going to continue with the numbering system to try and figure out other highlighted things, the other one being carbon 9. 9. And 9 here we can see is connected to 4. So this right here must be carbon 4 as I just labeled it. So you can now start to see that the carbocation was on 2, but now it's going to be on 4. And we can number around the rest of the chain, 5, 6, 7, and 8. And the reason I'm going through all of this is so we can be really clear about which bonds are going to be broken and which ones are going to be formed. And I'm going to try my best to highlight the different parts of the molecule. We can see here that let's see, the main difference. Okay, the main difference here is in the starting material, there's a bond between 4 and 8. No more bond between 4 and 8 in the products. What we do have now that is different is now we have a bond between 8 and 2. So we need to specifically break the 8-4 bond and form the 8-2 bond. The way that we'll do this is by starting at the 8-4 bond. That's why we went through all this trouble. The 8-2 bond, and whether you go to the carbocation or if you just go to there, either one is fine. So that's one way of doing it. You also could have numbered it a different way. So I'll just erase all of the numbering stuff, but this is one way of doing it, starting at the 8-4 bond and ending at 2. So now 8 is in a bond with 2, and 4 lost electrons and didn't get any back, and that's why 4 has a carbocation. It would have been just as correct to show your arrows like this. That does essentially the same thing because of the symmetry plane in that molecule right there. And hopefully I have battery life to complete this next problem here. It's the last one on this page. We start here at the electrons on, pardon me, we start at the electrons on the pi bond and we end at the hydrogen. Those two electrons get kicked over to bromine. Now, curved arrows weren't necessary in this particular step, but I think it's helpful to remember how this goes. And in a more simple term, you have the option of adding a hydrogen to either one of these carbons and putting a carbocation on the other one. And what we're looking for is a more stable carbocation. So the tertiary carbocation is formed, and the newly added hydrogen went to, in this case, the primary carbon. So whether or not you actually drew out that hydrogen doesn't really matter. Even if we just drew this structure here and showed it was a tertiary carbocation, that would be great as well. So that's page 2. If you want to go over version B, once again, that's in a separate video. Thanks for listening and watching.